Introduction to Quantum Information Processing. Welcome to Lecture 12. In this lecture, I will show you Grover's search algorithm. This algorithm solves several search problems quadratically faster than currently known classical algorithms. Moreover, in a certain black box setting, it can be proven that the speedup attained by Grover's algorithm is quadratic with respect to what is possible by any classical algorithm. Although quadratic improvement is less dramatic than the exponential improvement possible for, say, factoring, Grover's algorithm has wide applicability to many problems. Let's begin by defining an abstract search problem. You are given a black box computing a function f from n bits to 1 bit. Here's what the black box looks like in the classical case. I've put the query in reversible form following the standard method from Lecture 6. So the query is a bijection on the set of n plus 1 bit strings. And here's the black box as a unitary operation on n plus 1 qubits. Your goal is to find an input x in the domain of f such that f of x equals 1. This is called a satisfying assignment, or satisfying input, because it is a setting of the logical variables so that the function value is true, denoted by the bit 1. It is possible for the function to be the constant 0 function, in which case there does not exist a satisfying assignment. In that case, the solution to the problem is to report that f is unsatisfiable. There is also a related decision problem where the goal is simply to determine whether f is satisfiable or not. For that problem, the answer is 1 bit. How many classical queries are needed to solve this problem? Please feel free to pause to think about this. It turns out that 2 to the n queries are necessary in the worst case. If f is queried in only 2 to the n minus 1 places, and the output is 0 each time, then there's no way of knowing whether f is satisfiable or not without querying f in that last place. Remember back in Lecture 6, we saw that there can be a dramatic difference between the classical deterministic query cost and the classical probabilistic cost? For the constant versus balanced problem, we saw that exponentially many queries are necessary for the worst case, but that there is a classical probabilistic algorithm that succeeds with probability, say, 3/4, using only a constant number of queries. So how does the query cost work out for the search problem? What's the classical probabilistic query cost if we need only succeed with probability 3/4? Please pause to think about this. It turns out that order 2 to the n queries are still needed. Suppose that f is satisfiable in exactly one place that was set at random. Then by querying f in random places, on average, the satisfying assignment will be found after searching half the inputs. So the expected number of queries is around 1/2 times 2 to the n. Based on these ideas, it can be proven that a constant times 2 to the n queries are necessary to find x with success probability 3/4. So asymptotically, it's just as hard with probabilistic algorithms. What's the quantum query cost? That's order square root of 2 to the n by Grogers algorithm, which is the topic of this lecture. Notice that the query cost is still exponential. The difference in the exponent is only by a factor of 2. But this speedup should not be dismissed. If you're familiar with algorithms, then you are probably aware of clever fast sorting algorithms that make n log n steps instead of the n squared steps that you get if you use the most obvious sorting algorithm. The improvement is only around quadratic, but for large n, this quadratic improvement can make a huge difference. Similarly, in signal processing, there's a famous fast Fourier transform algorithm whose speedup is again quadratic over trivial approaches to the same problem. A natural application of Grogers' algorithm is when a function f can be computed in polynomial time, say time n to the c for a constant c. So there is a quantum circuit of size n to the c that implements an f query. Then we can use Grogers' algorithm to find a satisfying assignment with order square root 2 to the n times n to the c elementary gates. For several NP-complete problems, this is quadratically faster than the best currently known classical algorithm. The order finding and factoring algorithm make use of interesting properties of the Fourier transform. Grogers' search algorithm makes use of the properties of much simpler transformations. Consider the two-dimensional plane. There's a transformation called a reflection about a line. The way it works is that every point on one side of the line is mapped to a mirror image point on the other side of the line like this. Here's another example of a point being mapped to its mirror image with respect to the line. Here are more examples. Okay, so I assume that you have an intuitive understanding of what a reflection about a line is. Now, suppose that we have a second line. We can define a reflection operation with respect to that line. Suppose that the angle between the two lines is theta. What happens if you compose the two reflections? That is, you apply reflection 1 and then reflection 2. Let the origin be where the two lines intersect. And suppose we have a vector from the origin. This vector makes some angle. Call it theta 1 with the first line. After we perform the first reflection, the reflected vector makes the same angle theta 1 on the other side of the line. The reflected vector also makes some angle with the second line. Call that angle theta 2. Notice that theta 1 plus theta 2 equals theta. Now, if we apply the second reflection, then the twice reflected vector makes an angle theta 2 on the other side of the second line. So what happened to the original vector as a result of these two reflections? It got rotated by angle 2 theta. Notice that the amount by which it got rotated just depends on theta. It does not depend on what theta 1 and theta 2 are. This is an illustration of the following lemma. For any two reflections with angle theta between them, the composition of the two reflections is a rotation by angle 2 theta. The picture above is intuitive, but is not a rigorous proof. You can either take my word for this, or you can prove it rigorously on your own as an exercise. The methodology is to express each reflection operation as a 2x2 matrix and then multiply the two reflection matrices. The result will be a rotation matrix by angle 2 theta. This simple geometric result will be used in Grogers' algorithm. Grogers' algorithm is based on repeated applications of 3 operations. One operation is the F query that we're given as a black box. Another operation that will be used is one that we'll call U sub 0. In the computational basis, this flips the target qubit if and only if all the control qubits are in state ket 0. For other computational basis states, it does nothing. As an aside, we might think about whether or not this is easy to implement in terms of 1 and 2 qubit gates. U0 is similar to an n-ary Toffoli gate, which flips the target if and only if n control qubits are all in state ket 1. But it should flip if and only if all control qubits are in state ket 0 instead. This is achieved by conjugating the n-ary Toffoli gate with NOT gates. But how can we implement the n-ary Toffoli gate in terms of simpler gates? I'll leave this as an exercise which you should feel perfectly free to take a pass on. But if you're interested in pursuing this, then this can be done with order n 1 and 2 qubit gates. A hint is to use ordinary Toffoli gates, and you can also use an ancilla qubit as part of the computation. A third operation that we'll use is the n-qubit Hadamard gate, by which we just mean the n-fold tensor product of 1 qubit Hadamards. So the tensor n in the exponent is implicit in these gates. Also, we will use the UF and U0 gates with the target qubit set to the ket minus state, which causes the function value to be computed in the phase. For U sub f, this means that ket x picks up a phase of -1 if and only if f of x equals 1. For U0, this means that only the ket of the 0 string picks up the phase of -1. Here's what the main part of Grogers' algorithm looks like. It starts with a preliminary step, which is to apply h to the state of ket zeros. Next, what we'll call the first iteration occurs. This is the sequence U sub f, h, U0, and h. Then a second iteration, which is the same sequence of operations, occurs, and so on. Here's a summary of the algorithm in pseudocode. K iterations are performed, and then the state of the first n qubits is measured in the computational basis to yield an n-bit string x. Then a classical query on input x is performed to check if f of x equals 1. If it is, then the algorithm has solved the search problem. You might notice the minus sign in the iteration in the pseudocode. This is just a global phase, but it will make the geometric picture of what the algorithm does look nicer. What is k, the number of iterations, set to? This is an important issue. We will determine this later on. What I will show you next is that U sub f is a reflection, and the sequence h, U0, h is also a reflection, and then we'll be able to apply our lemma about composing two reflections to get a rotation. The function f partitions the set of n-bit strings into two subsets. Define A1 as the set of n-bit strings on which f takes the value 1, the satisfying assignments. Define A0 as the set of n-bit strings on which f takes the value 0, the unsatisfying assignments. Let capital N denote 2 to the lowercase n, the size of the search space. Let S1 denote the size of A1, the number of satisfying assignments, and S0 denote the size of A0. So note that S1 plus S0 equals n. Bear in mind that if f has many satisfying assignments, for example, if half the inputs are satisfying, then it's easy to find one with high probability by just random guessing. The interesting case is where there are very few satisfying assignments to f. To understand Grogers' algorithm, it is useful to focus our attention on the case where S1 is at least 1, but much smaller than n. For example, if S1 is 1 or a constant. In that case, finding a satisfying assignment is challenging. Now, let's define two quantum states. Let ket A1 be the uniform superposition of all elements of A1. That is, the uniform superposition over satisfying assignments. And let ket A0 be the uniform superposition of all elements of A0. Notice that these two states are orthogonal. Consider the two-dimensional space spanned by ket A0 and ket A1. The state after the preliminary Hadamard operations is within this two-dimensional space. It's a linear combination of ket A0 and ket A1 with respective coefficients, the square root of S0 over n and the square root of S1 over n. These coefficients are the cosine and sine of some angle that we'll call theta. In the case where S1 is greater than or equal to 1 but much less than n, theta is a very small but positive angle. If the system were in state ket A0, then measuring it in the computational basis would yield a random unsatisfying assignment. The system is actually in the state h of 0, which is very close to ket A0. Measuring that state in the computational basis results in an unsatisfying assignment with high probability. Imagine if the system were in state ket A1. Then measuring it in the computational basis would yield a satisfying assignment, a random satisfying assignment. So if we can somehow move the state close to ket A1, then measuring will yield a satisfying assignment with high probability. So a useful goal is to somehow move the state towards ket A1. Notice that although the states ket A0 and ket A1 exist somewhere within the 2 to the n dimensional space of all states of n qubits, the algorithm does not have information about what they are. It cannot perform a rotation matrix directly without knowing what these states are. Now I'll show you how the iterative steps in Grogers algorithm perform this rotation. The iterative steps I mentioned before consist of two reflections. The first reflection is U sub f. This is a reflection about the line passing through the vector ket A0. Why? Because U sub f applied to ket A0 results in ket A0, and U sub f applied to ket A1 results in minus ket A1. The second reflection is minus h U0h. This is a reflection about the line passing through the vector h of 0. To see this requires a bit more analysis. Here's a proof. First, we can show that the state h of 0 doesn't change under this operation. Second, we can show that any state orthogonal to h of 0, which I'm denoting as h of 0 perp, picks up a phase of minus 1 under this operation. So each iteration is a composition of two reflections, and the angle between them is theta. Therefore, each iteration is a rotation by 2 theta. The effect of k iterations is to rotate by k times 2 theta. What should k be set to? How many iterations should the algorithm make to move the state to ket A1? First, let's consider the case where there is one satisfying assignment, that is, where S1 equals 1. In that case, sine of theta equals 1 over square root n. Since 1 over square root n is small, This means that theta is approximately 1 over square root n. Then setting k to pi over 4 square root n, rounded to the nearest integer, causes the total rotation to be around pi over 2 radians. That's about 90 degrees. The resulting state will not be exactly ket A1, because that's likely a state between two angles. But it will be close, so measuring will produce a satisfying assignment with high probability. The resulting algorithm makes order square root of n queries, one per iteration, and has high success probability. Remember that this is for the case where f has one satisfying assignment. What if f has more than one satisfying assignment? One might be tempted to think that intuitively the hardest case for the search is where there is just one satisfying assignment. So maybe the algorithm performs at least as well when there are more satisfying assignments. Could that be the case? Unfortunately, no, it doesn't work that way. Suppose that there are 4 satisfying assignments. Then the value of theta is double the value of theta for the case of one satisfying assignment. Therefore, the rotation overshoots. The total rotation is by 180 degrees instead of 90 degrees, which is no good. The state starts off almost orthogonal to ket A1, then midway it gets close to ket A1, and then it keeps rotating and becomes almost orthogonal again. When there are 4 satisfying assignments, the ideal number of iterations is half the number for the case of one satisfying assignment. The situation is kind of analogous to baking a cake or a souffle. You should not underbake, but you also have to be careful not to overbake. If we know the number of satisfying assignments that f has in advance, then we can adjust k to be just the right value for the angle theta. But what if we do not have this information? What if we do not know how many satisfying assignments f has? What do we do then? It turns out that this is an interesting problem. Let's consider the various success probabilities for different numbers of iterations between 0 and pi over 4 square root n. If there is one satisfying input to f, then the success probability as a function of the number of iterations is this sinusoidal function. The success probability is close to 1 when pi over 4 square root n iterations are applied. If some smaller number k of iterations is applied, then the rotation is less than 90 degrees, and the point on the curve indicates the success probability, which is the projection squared of the state onto ket A1. And here's the curve for the case where there are 4 satisfying inputs. You can see that the success probability is around 1 at the halfway point, but then it declines towards 0 after pi over 4 square root n rotations. At this point, you might wonder if maybe measuring midway through and at other intermediate stages is a good idea. But once you measure, the state collapses, so you cannot measure and then continue the iterations after the measurement. Once you measure, then you can only continue by starting from scratch. Here's the curve for the case of 2 satisfying inputs. In that case, pi over 4 square root n iterations overshoots, but not by so much. There's still a non-negligible success probability. Here's the curve for 3 satisfying inputs. And here's the curve for 6 satisfying inputs. In that case, the rotation is by more than 180 degrees. And here's the case of 100 satisfying inputs. In that case, theta is 10 times as large as the case of 1 satisfying input. So there are 5 ups and 5 downs, each corresponding to a rotation by 90 degrees. So how do we choose a good number of iterations k that works well for all possible cases. For any given k, there will be cases where the success probability will be small for that number of iterations. An idea is to choose k randomly between 0 and pi over 4 square root n. In that case, the success probability is the average height of the curve over its range. This is kind of like the area under the curve. In the case of one satisfying input, by the symmetry of the shape of the curve, we can see that the area is 1/2. So that will be the success probability. What about the case of two satisfying inputs? What's the average area under that curve? Averaging for the 90-degree rotation, we get half of that region. Then averaging for the remaining partial rotation, you can see that it's more than half of that region. So the overall success probability is more than 1/2. It's also more than 1/2 for the case of 3 satisfying inputs. For the case of 4 satisfying inputs, it's 1/2 again. Let's look at the case of 6 satisfying inputs. For the first 2 90-degree rotations, it's half of that region. Then, for the remaining partial rotation, it's less than half of that region. So the overall average is less than 1/2. The average can be calculated to be around 0.43 for that case. It turns out that the case of 6 satisfying inputs is the worst case. When there are more satisfying inputs, the last partial rotation comprises a smaller region, so it has less effect on the overall average. So choosing k randomly within the range results in a constant success probability that's at least 0.43, regardless of the number of satisfying assignments. That's one way to solve the case of an unknown number of satisfying inputs to f. To summarize, we have a quantum algorithm that makes square root of n queries and finds a satisfying assignment with constant probability. By repeating the process a constant number of times, the success probability can be made close to 1. What happens if there is no satisfying assignment? In that case, the algorithm will not find a satisfying assignment in all runs, and the appropriate output in that case is unsatisfiable. If there are many satisfying assignments, then using a refined version of this algorithm, a satisfying assignment can be found with fewer queries. The number of queries can be order square root of n over s1, where s1 is the number of satisfying assignments. Note that we are assuming that the value of s1 is not known. So we don't know in advance how long the algorithm will run for. I won't get into the details of this refinement here. Finally, you might wonder if Grover's search algorithm can be improved. Could there possibly be a better quantum algorithm that performs the black box search with fewer than square root queries? Actually, no. It can be proven that the above query costs are the best possible. The proof of this will be the subject of Lecture 13. Okay, let's end this lecture now.